met me.
Hi, Taylor.
I'm Taylor. I'm one of the new chairs for the ARC seminars, inheriting from Nick, Elijah, and I.
Cheers, Mark.
Okay. We're your new czars. But yeah, so to kick us off for our first comeback seminar, it's going to be Jiaxi talking about GRMHD. I'll give it a little intro to that. So,
Okay.
yeah.
Yeah, so I think for people don't know what I'm doing, so basically I run simulations, and specifically GRMHD simulations, and the objects that I'm interested in are neutron stars, black holes, coupled to matter, and systems like that. And so first of all, what is GRMHD? So it's actually composed of three forms. First one is GR, so you have to have some compact objects which has strong gravity effects or relativistic speeds. So for example, you may have black hole, you may have neutron stars, supernovae, or you may have like the jets, which travels in at least intermediate relativistic. And we should also have magnetic field and often strong. So for example, in Earth's atmosphere or in Earth's magnetosphere, the magnetic field is not very strong. And in that sense, it's not a very big problem, but in pulsars, where magnetic field could be 10 to the 12th gauss, and magnetized could be 10 to the 16th, it's ultra high magnetization. And the third part is the hydrodynamics. That is the matter. So for example, for some SXS colleagues that are doing binary black hole mergers, that's probably in vacuum and there's no matter inside, so they need to evolve the full Einstein's equation in different formalisms. But now we have matter, so you have to couple the Einstein's equation to, for example, the fluid dynamics or the Maxwell's equations and just solve them all together. So I borrowed the left image from Yunsu's talk 1 year ago. So basically you have a black bear and a polar bear, and then merge them together to get the magnetohydrodynamics. And then you put this panda into the vicinity of black hole accretion disks, it'll be GRMHD. Okay, but so I made the right image asking ChatGPT, and obviously it doesn't realize that the panda should be stretched. Yeah. Okay, so where do we apply GRMHD? So basically, we may apply it to a black hole accretion disk system, the lower left panel, where relativistic jets might form, like if you're familiar with the BZ Blandford-Znajek effect, where you extract the rotational energy from black hole and to power the jets. And we may also apply it to binary neutron stars because neutron star is not vacuum, it has matter and finite density. Or we can apply it to a supernovae, pulsar, where the proton-neutron star might emerge from it, and there are also ultra-relativistic speeds, particles, and fluid elements. So one key question is why we can model astrophysical plasma as fluid. So basically, when we talk about fluid mechanics, we're in a scale that is much larger than the microphysical scale. And the fluid element is also in a much smaller scale than the problem that we care about. So basically, fluid mechanics is a collective behavior of like a chunk of particles moving together. And the particles' mean free path should be much smaller than the scale of the problem we care about, so that it's collisional. It can transport energy and momentum due to these collisions and make them moving all together. So, and another key thing is that we should in thermodynamic equilibrium so that we can apply the equation of state and evolve them steadily, quasi-steadily. And so there are some cases where the MHD approximation might fail. For example, in solar wind or particular part of the ISM, the plasma is no longer collisional. The mean free path is very long, and we have to solve full Vlasov equation. So Vlasov equation actually is a 6D equation. So in a phase space, you have 3-dimensional of your displacement. you have 3 dimension of your momentum. So you solve the distribution of C60. And it's obviously much more complicated than MHD because it's a single fluid model and it needs extra computational resources. Or when you are caring about small scale behaviors, which I will talk a little more about magnetic reconnection later, but in small scales, there are resistivity and other non-ideal phenomena in the fluid so that we cannot treat them as pure fluid and solve with ideal MHD. And and also for ultra-strong magnetic field or turbulence, we have to treat them separately. So let's get started from MHD. I'm not sure whether all of you are familiar with hydrodynamics, but the first 2 equations are essentially hydrodynamics. The first one is conservation of mass, or the continuity equation, and it's in a local form. So if you do a volume integral of it, it will be the time derivative of mass equals to the mass flux. And the second equation is just the equation of motion, where the right-hand side is some effective forces. For example, grad P is the pressure, and J cross B is just the Lorentz force, QVB stuff. And the third equation is the evolution of magnetic field. So normally we treat magnetic field using Maxwell's equations, while we do a curl of, let me maybe write it out. We got curl of E equals something, curl of B equals something. And this, right, so we do the curl of this term. And the curl of E could be substituted with the first equation, and we get a time-evolved equation of E field. So basically, there's where the induction equation is getting from. And we can see that, for example, here is velocity. So the motion of your fluid is coupled to the evolution of your magnetic field. And in the evolution of equation of motion, also you have magnetic field coupled to your evolution of your fluid system. So the EM part and the hydrodynamic part are coupled together. And we also have 2 divergence theorem in the Maxwell's equation, and one of them is the constraint of magnetic field. So all of these different equations coupled together close the system, and we want to solve the system eventually. Okay, so now let's move to the GR spacetime. It's a direct comparison between the Newtonian MHD and GRMHD, because essentially you just need to change the time derivative and the divergence term into covariant derivative. So for example, this one is conservation of mass, conservation of energy and momentum, Maxwell's equations. So the F here are the Faraday tensor, and then special relativity is just a 4 times 4 matrix made up of E field and B field. And the T here is for stress energy tensor. So basically, in MHD, it's made up of 2 components. One is the fluid component, and the other is the magnetic field component. So these are the systems that we want to solve. And how should we solve it? I think this is familiar to most of the GR people.
Can I ask a question actually before
yeah.
So I seem to remember in non-relativistic MHD, there's this approximation that you neglect the displacement field, like displacement current, right?
The displacement current, you
So
mean?
like the dE dt in the Ohm's and the Ampere's law.
Yes, that's right.
So
Because,
like because in non-relativist MHD, this is because it's like some higher order V over C or something, right? So like what happens to that in relativistic, like?
So basically, we do not neglect them because in the covariant form, the Faraday tensor includes every component of it.
Mhm.
And later on, when we decompose this covariant form into 3+1 formalism, we can neglect some terms that we don't know, we do not care about or have like negligible effects.
Okay, yeah.
So yes, so 3+1 decomposition of space-time. So why should we do this? So basically, in, for example, undergrad computational physics class, when we want to evolve a system, we have a time component, d over dt, something, the evolved variable. And on the right-hand side, we have some spatial derivatives or just ordinary terms. And what we do is to discretize the time step as well as discretize the spatial grid, so that we can get the value of the evolved variable at next time step computed from other quantities at the first time step. So if your equation is in covariant form, it's actually no like obvious distinguish like between the time component and the spatial component. So the first thing that we want to do is to decompose the 4-dimensional space-time into 3+1 dimension. And the 3D component is the hypersurface or space-like component, and the 1 component is the time-like time component. So in this figure, each slices here, sigma t and sigma t plus dt is the hypersurface, and the n vector here is the normal vector, which is actually the time vector. So the real time vector in this decomposition will be the green line. It is composed of your normal vector plus a shift. So yeah, basically you can imagine, like, for example, in a uniform inertial frame, uniform moving inertial frame, the shift vector could just be the velocity of uniform motion. And then it drags the flat 3D space along with it. But in GR, it could be more complicated. For example, in a space-time of a curved black hole, the shift vector could be doing some rotation around black hole to make it simpler. So now we have 2 different choices to do the decomposition of other quantities, except from like space-time. So for example, we can do something called Eulerian decomposition. So Eulerian means that the normal vector is n. It's the pure space-time decomposition. And we can decompose the full velocity, for example, this u, and also other quantities, into some component parallel to the normal vector, and some component projected onto the hypersurface. So this v mu object is purely spatial, which means v superscript 0 equals 0. And v superscript 1, 2, 3, which are the spatial components, are not 0. And in Eulerian frame, for example, the Faraday tensor could be decomposed into this second equation, some normal component of E, and some spatial component of B. While another decomposition, so I have to mention something earlier. So the alpha and beta terms here are gauge terms. So it means that you can choose them arbitrarily and doesn't change the physical interpretation of your system. Just like the lambda and phi terms in, vector potential A and potential B terms in E and M. There's a gauge freedom here as well. So actually we can change the normal vector into the fluid frame, which is the U. So U is the full velocity of your fluid element. We can change to a co-moving frame with the fluid element and decompose everything into that frame. That's the first equation. Now the normal vector is changed to the full velocity vector of your fluid, and to decompose it into a co-moving electric field and co-moving magnetic field, which are lowercase quantities. So any problem about this? Questions? Yeah.
So n is the normal.
Yeah.
And so that's the Eulerian.
Yeah.
U, how do you think of U? Is that kind of more of a tangent, or is it?
So basically, if you have a like 4D spacetime, and you have U, it's just a curve in that spacetime, and you follow this curve and expand your spacetime in the co-moving frame of that curve. That's it.
Okay, so U is tangent to that arbitrary curve that you have.
Yes.
Okay.
Yep.
I guess with the uppercase and lowercase b, in those cases, is that just to differentiate the different magnetic fields, or is lowercase b something else?
So yes. So the lowercase is the magnetic field measured in the co-moving frame of the fluid.
Okay.
And the upper one is the magnetic field observed in like the normal 3+1 decomposition.
Okay, so it's just uppercase, lowercase, base.
Yeah.
Okay.
Yeah. Because in the code, normally these are the two like frequently used decomposition method.
Mm-hmm.
You could also like change, like there's a gauge freedom. You can change the n to anything.
Yeah.
And that'll yield a different decomposition as well. It might be some other e, but yeah, these are the two that we use.
Right, and also, so just to ask, just make sure, as like a non-relativist, I'm interested in like Newtonian limit. So the Newtonian limit is because U is basically n.
That's right.
Right.
That's right. Yeah.
So
U, no, I think U is perpendicular to n.
Oh,
Yeah.
and n is the
Sorry.
is the normal.
And n is in the time direction.
okay.
N becomes trivial, just a unit, like
Mm-hmm.
trivial in the Newtonian limit, because you don't have a curved thing, so you'll never, your next hypersurface will never be offset from your current hypersurface thing.
So n will be -1, 0, 0, 0.
Right, but sorry, so I thought that in the like co-moving frame, the forward velocity is just like 1, 0, 0, 0 or some such thing,
Mm-hmm.
right?
That's right.
And then so like it becomes other elements become like non-zero when you're not in the
Mhm.
same frame, right?
Yeah.
But then if you're in the Newtonian limit, then basically you're saying the other terms are negligible, right? So why are they not the same? Why is n not u in that limit?
So a Newtonian limit.
U would be, the
One
spatial part of U
V.
would be very small.
That's what I mean, yeah. So I'm saying like the Newtonian limit is when n is equal to u, or is that not the correct?
No, so in Newtonian limit, n is 1, 0, 0, 0,
And
while
is-
u is 1 vx, vy, vz.
which are negligible, right?
Yeah, yeah, but it's not the same thing.
Right, okay, fine, yeah.
Because it's only negligible in relativistic case if your like speed is very small. But let me see.
Maybe it's more some. Like somehow, like in the Newtonian limit, should f mu nu just be one number, one tensor, right?
In
Or
Newtonian
no.
limit, f
Or
mu.
maybe not actually. Never mind. Sorry, I see.
It means like no GR, no SR.
No GR, no SR. What happened? Well, I guess I see how they should be different. Yeah. Okay. Never mind.
So now we come to the question of how do we solve these equations. So one most important thing in solving equations numerically is to make sure that the equation is stable in terms of numerical evolution. So that means that you should write your equations in a hyperbolic formalism. And here actually, it means that it should be written in this kind of form. And u could be any evolved variables that you care about. And you have to make sure that the coefficient matrix A is diagonalizable and gives you real eigenvalues. So what we are going to do next is to try to write those covariant form equations into this one with the help of 3+1 decomposition. So here is one example. The continuity equation. The first equation is just something well proved. so you can write the covariant derivative or divergence of some term into 1 over square root minus g partial derivative of mu square root minus g and the original 4 vector. And so is everyone familiar with how GR works here? Not really?
In passing.
Sorry?
Like not well.
It's just like the index notation.
Oh yeah.
Okay. So basically, you have like lower index and upper index. You just iterate over all the possible choices. So you have partial t and partial I, and ut and ui. And so you can see that ut and ui can be written in terms of the decomposition. Let me recall you of this. So ut is wnt plus vt, where vt is 0, as I said, because it's the projection onto the hypersurface. And ui should be wni plus vi. So we can write this u into ut and ui, and it both gives you the equation like partial t something plus the 3D divergence of some other quantities equals 0. And that's the hyperbolic form. So the quantities that in the time partial derivative, d, which is equals to like rho w, is called conservative variables. So basically, you can imagine that the second term of this equation is a flux term, right? So you have a divergence of something, and use Gauss's theorem, you can turn it into the flux over through a surface. And then the left-hand side is just the time change of that variable, and just like the continuity equation, dm over dt equals mass flux. So this one is called conservative variables because mass is a conservative variable, and at least in a global sense. So similarly, we can write other covariant equations like the stress energy momentum equations and the Maxwell's equations into this one. So the calculation is rather complicated, but the key thing in mind is that we have a set of conservative variables, u, which are defined as d, sj, tau, and bk. And we have the flux terms and the source terms. And this is exactly a hyperbolic equation that we can solve numerically and stably. So you may have already noticed that the conservative variables are not fundamental in the sense that, for example, d is rho w, where w is the Lorentz factor, so 1 over square root 1 minus v squared. So d is composed of density and the 3 velocity component, and for example, s is composed of density, v, and e and b, and this h is specific enthalpy. Let me write it down. So specific enthalpy is 1 plus epsilon plus so epsilon is the specific internal energy, T is pressure, and rho is density. So the real fundamental quantities are those densities, velocities, specific internal energy, and magnetic field. And those conservative variables are actually nonlinear combinations of these more fundamental, or what we call it, primitive variables. And also for the flux term, they are made up of primitive variables, and the source term is made of primitive variables. So as you can imagine, that if we have the primitive variables, we can calculate the conservative variables easily, and we can calculate the flux term, the source terms, and evolve the system to the next step. But at the next step, what we get is the value of conservative variables, but not the primitive variables. So we need to convert the primitive variables, convert from the conservative variables to primitive variables at next time step. And this is one of the difficulties in GRMHD code, and I'll talk about it more later. Yeah.
From the previous slide to this one, you have the square root of the determinant of the metric go from minus g to gamma.
Mm-hmm.
What is that?
So if you write out ut, I would just give a example of this. If you write, can I write here?
Yeah, people on there won't see, but that might be fine. We can rotate the.
Oh, okay. Yeah, you can go. So basically, ut is wnt plus vt, and vt is 0, and wt is 1 over alpha. Let me remind you of this here. U superscript t is 1 over alpha. So now your square root minus g rho ut would be square root minus g over alpha rho w. And this is square root gamma rho w.
Ah, okay, because
Yes.
the time component of g is
That's right.
minus alpha. Right. Yeah. Okay.
So basically, we can write everything into a square root gamma later, because there will be nt here in every decomposition, and there's 1 over alpha that eliminates the square root of minus g. Okay. Any other questions? So this one is not my specialization. I think Kyle or people in SSS group is like more familiar with it.
I know it exists.
Yeah. But anyway, so we have to couple our MHD equations to GR equations. And there are different formalisms of how we solve the Einstein's equations. One famous one is the BSSN equation, formalism, sorry. And one, like most recently, frequently used is the Z4C evolution system. So basically, what we need to do with these space-time evolution is to calculate the metric, the evolution of the metric, and then couple it to, for example, here when you need alpha, you need beta, you need square root gamma, have to calculate those metrics. Okay. So, got 20 minutes. So I would talk briefly about the numerical implementation of the GRMHD equations. And I would talk about it in the most simple one, which is ideal MHD limit, where you don't need a separate evolution equation of electric field, because in ideal MHD limitation, in ideal MHD limits, the plasma is considered to be a perfect conductor, which means there is no resistivity, and your E field could be expressed as some minus V cross V. It's a combination of velocity and B field, so you don't need to write it separately. So, but here, let me give you like the most general steps of one-time step evolution. So first, you should get metric variables and enforce those like Hamiltonian momentum constraints on the matrix from the space-time evolution module. So those are two separate modules. You can evolve space-times alone or MHD alone, but when we couple them together, we should first get the metric variables from the GR sector. And then we need to reconstruct the variables. So what do I mean by reconstruct? Is that you have two cells, let's say. And as I said, the flux term will flow through the cell interface. So basically, you need to know the primitive variable values at the cell interface instead of at the cell center. That's called reconstruction. And the flux is calculated by the Riemann problem, Riemann solver here. So yeah, these are the two steps. And then we can update the conservative variables once we have the flux calculated, and we need to enforce the divergence-free condition for the magnetic field. And after that, we apply primitive recovery, which is the C2P, which I will talk about later as well. And after that, we compute the stress energy tensor at the new time step and feed it back to the evolution of Einstein's equations. So that's a cycle. Okay. So here are the algorithms. So basically, reconstruction. Let me see. I can pull this up.
Oh, is it stuck on there?
Okay.
You just use this board.
Yeah.
Is it convenient? Just for, okay. So the reconstruction is when you have 3 cells and you want to know, so we have 3 data points here. These are the known points, and we want to know what's the value of these variables on the cell interface. So basically it's just some interpolation techniques, but you can make it ultra high order and make it ultra accurate. And there are 2 widely used methods. PLM means linear, so you get something like this. And the other one is parabolic, so you get a second order accuracy. But the difficulty of this is, so there's a term called high resolution shock capturing scheme that is at some discontinuities. It's very hard to recover this. So we have to reconstruct the variables carefully. Next step is to do a Riemann solver. So basically, now I have an illustration of this. So we have 2 cells, I minus 1 and I, and there's an interface, I minus 1 and 2. And we want to calculate the fluxes through this interface, because in the evolution equation, the fluxes penetrates over the interface instead of the cell center, right? Because you apply Gauss's theorem and it's the flux over the interface. So basically, Riemann solver does this. And you got a left state, which is reconstructed from this indexed I cell, and you get a right state, which is reconstructed from I minus 1 cell. And then you calculate the fluxes. The calculation can be very different and difficult for different different evolution equations. But the difficulty lies in that in GRMHD, when you calculate the wave speed of this, there are 7 wave modes, and it's very hard to distinguish between them. Yeah, so Riemann solver is one of the undersolved problems right now. There are a couple of famous ones, but I think at least Sarah is still doing Riemann solver problems. And the third algorithm is constraint transport. So this actually guarantees that the B field is evolved divergence free. So how we do that is that instead of having cell-centered value for other material variables like density, the pressure, they're all cell-centered, we staggering the B field to face-centered. So there will be 6 values of B in a cube instead of 1. And by applying Faraday's law, the flux of magnetic field is the loop integral of the surface boundary. So, for example, let's look at this face. The loop will be to the left for the upper edge, while for the upper face, the loop will be to the right for this upper edge. And when you add the fluxes from 6 faces together, these 2 terms will eliminate each other, and the right-hand side will be 0. So you apply the Gauss's theorem again, the divergence of B is 0. That will automatically guaranteed divergence-free constraint, and this is called constraint transport. So in a GRMHD code, B field now is like staggered onto each phase instead of in each cell. So there is a quite different storing scheme for B field and other fluid variables. And like I said, the reconstruction and Riemann solver, if you have cell-centered values, should be reconstructed on cell interfaces, which are the phase. But if you have phase-centered values, the reconstruction Riemann solver should be calculated on edges, which are the interfaces of phase. And the last thing is the primitive recovery. So basically we have a set of cons and a set of prim, and that is non-linearly coupled to each other. There are some specialized methods to reduce the number of non-linear variables, or to like separate different subsets of cons and prim variables so that we can solve it easier. But in general, there is no guaranteed solution of cons to prim conversion. And sometimes you'll get unphysical solutions. For example, you might get negative density, negative pressure, or ultra high magnetization level, ultra high Lorentz, or even superluminous velocities. So we have to apply some flooring scheme to the C2P results. For example, we have to raise the density to at least some finite volume, non-negative finite volume if it's too low. And we have to apply some cappings. For example, you cannot get Lorentz factor too big, normally 30 or 50, and also the magnetization level to ensure the stable numerical evolution. So for these 4 algorithms, each is, I think reconstruction is easy, but for the rest 3, each is very difficult and it's still interval.
Can I ask a question?
Yeah.
For constrained transport, you said you preserve the divergence-free nature of the field at machine precision.
Yeah.
Does that mean practically that you never have to do divergence cleaning, or does it mean you just do it less, or
You never need to.
you never
Yeah,
need to?
because it is guaranteed by mathematical form.
Sure. Yeah. You don't like accumulate error or something.
No.
So staggering the magnetic fields on the sides, basically.
That's
that's
nice.
nice.
Yeah. It's a very clever.
Yeah, that's
Yeah,
yeah.
that's nice.
Yeah.
It costs those 6 times more space.
Still clever.
6 times more clever.
Yes.
Okay, so what I've talked about is the most fundamental GRMHD equations. So we can absolutely add more physics, but at high costs. So first thing is the resistivity. So basically, let me draw something. So you can also see the lower left image. That if you have a magnetic field line going to the right and another going to the left, while this separation scale is quite small to your simulation scale or your grid scale, or comparative to. That would cause a current sheet. So this is B field. If you apply, what is it called? The right-hand rule. There is a current flow inside to the board. So this current sheet will have finite conductivity. It's not infinite conductivity anymore. And you have to apply resistive force in this current sheet, and the magnetic field line will eventually reconnect each other and release energy. So for resistive MHD, we have to add evolution equations of electric field. So instead of just 8 variables, you have density, 3 velocity, energy, and 3 magnetic fields, so 8 variables. you have 11 right now, so you have 11 equations, much more complex. Another microphysics that we can add is viscosity, and it's very important in things like accretion disks or the outer region of the binary neutron star merger, the hypermassive neutron star, where angular momentum are effectively transported out with this viscosity. And also imagine that, I can also use this plot, you have a flow, it's no longer being right now. You have a flow to the right and you have a flow to the left, and there is a shearing layer between this where instabilities can grow. So you might get some turbulent behavior here, like mix these two different components of the fluid, and in that case we need viscosity. And also for specific simulations such as supernovae, core collapse supernovae, or binary neutron star mergers, we need neutrino physics because there are R process, like R process is basically rapid capture of neutrons. So you have imagine a nuclear core that you have much more neutrons than protons. That is unstable and it will decay by beta decay to emit neutrinos. So in binary neutron star or supernovae, there are extremely large numbers of neutrinos emitting from the collapsing core or from the colliding point that we need to resolve. And those neutrinos carry large amounts of energies outside, cooling the core and heating up the outer region. And by means of these heating, also from shock heatings, we need finite temperature EOS. So the most simple EOS is the adiabatic one. There's no temperature. And the next simple one is the ideal gas law. But eventually, in nuclear physics, there are a lot of tabulated 3D EOSs. 3D means the pressure is no longer just a function of energy and density and energy. It might be a function of density, temperature, and electron fraction. Or, as I heard this morning from Elias, there are even nuclear physics equation of state, including magnetic field strengths, which creates some like Langdell level something, I don't know what it is, but it's more complicated. And the last thing is some radiation transport. So how do you carry your energy out? But basically, all these microphysics can be added to the system by adding a stress energy tensor. So in the beginning, I write stress energy tensor as two components. One is the magnetic field, one is the fluid component. But you can also add a stress energy tensor for neutrinos, add a stress energy tensor for radiation field, things like that. And that will make the problem like much harder. So the current limitations, of course, the computational resources is not enough for us to fully resolve the problem. And I'll give you, because the time is in this, but I'll give you one simple illustration of this. So basically, what we are simulation is quite diffusive in scale. What I mean is that you need to worry about small scale effects such as magnetic field amplification. So imagine that two neutron stars close to each other, and they have this shearing layer because of different velocities. And here at very small scale, this is called Kelvin-Helmholtz instability, where amplification of magnetic field occurs here in small scales. And we have to resolve it in even scales of tens of centimeters in this scale. But on the other hand, if you want to extract gravitational waves, it's in a scale of, I don't know, hundreds of kilometers maybe, or even higher, thousands of kilometers. So you don't have that grid, like choices to both resolve the local instabilities and the global gravitational wave signals. So one way to go around this is the subgrid dynamo model, which effectively add here the alpha bj terms So add an exponentially growing magnetic field, which is not resolved by your grid resolution. And this alpha term can be obtained from local simulations. So for example, I first run an ultra high resolution local simulations that can capture the instability. And I don't care about the large scale structure. Now I obtain the growth rate of the magnetic field. Then I run a low resolution simulation, but containing a much more simulation domain, and I add this growing growth rate of magnetic field to my cell. And that will effectively enhance the magnetic magnetization level. For example, from here, can compare to the left-hand side images. The magnetic field is amplified effectively. And also you can see, find small structures that you cannot see if you just seed it with a big colloidal field. So, yeah. Yeah, so basically, this is one way to circumvent it, avoiding using ultra high resolution, but it's still not good enough, I would say, because for tens of centimeters, we still cannot fully resolve this KHI, so we don't know the alpha terms of KHI. Okay. So here are some summaries, and yeah, I think